Hello, everyone. Welcome back to the AAS YouTube channel, and this is part of the good stuff. This is the Sky and Telescope series, and I'm very happy to have Govert Schilling with us today. Hey, Govert.
Hi, Frank. Nice to be here, and thanks for having me.
This is great. So, what is your geolocation?
I live in the Netherlands, which is a small country in northwestern Europe. I know some Americans confuse it with Denmark. Well, we're pretty close, but it's a different country altogether. The Netherlands is famous for Amsterdam, obviously, and my hometown is about 40 kilometers east of Amsterdam.
I would imagine Amsterdam is a lot less crowded these particular days.
Actually, I was there yesterday.
Okay.
And since I haven't been there for a long time because of the COVID pandemic, obviously, but yesterday I had to be there, and it's very silent. It's almost empty. No tourists. Nothing's happening there.
Yep, very quiet. That is a pretty awesome telescope over your left shoulder.
Yeah, well, actually, that's my first telescope when I was a young kid, like 15 years old. I started out as an amateur astronomer. I had a job in a supermarket and saved some money to buy this second-hand telescope. And by now it's almost 50 years old, I guess. But still, it's still doing fine.
Do you still observe with it?
Not really, I have to admit. I started out with this hobby and did a lot of observing of the moon and the planets in particular. This was all well before the time of amateur photography. I've never been able to do that. So it was all visual observing. But later I started to write about astronomy for astronomy magazines, for newspapers, for whoever wants to read my stuff. And it became my job. And as you can imagine, if astronomy is your job and you have some free time, it is sometimes nice to spend your free time with another topic. So I'm not that active of an observer anymore.
That's cool. Yeah, you're.
But of course, I have to say that one thing every Sky and Telescope reader will know, that one thing that never leaves you is whenever you get out of the door at night, the first thing you do is look up to the sky and recognize the constellations and the stars. And obviously, when there's something special like a meteor shower, a lunar eclipse, a nice conjunction, I'll never miss it. So don't worry. It's not that I don't look at it anymore. It's just it's not my daily routine.
Right. So since you hinted at it, let me go ahead and ask. So when you're not doing astronomy or writing about astronomy, what do you like to do?
It sounds pretty dull. I love reading books. I love walking, a little bit of hiking, although the Netherlands, we don't have mountains, as most people will know. Our highest mountain, just for your information, is 360 meters tall. So, and we share it with Belgium and Germany. But I like to walk a lot, and I like reading books, and I like photography, not astronomical photography, but landscape, architecture, those kind of things.
Very cool. Very cool. So let's go ahead and talk a little bit about astronomy, since that's what your day job is. And we have this, your latest of many, really
in
lovely.
The May issue, right?
Yeah. Yes, this is going to be the May issue of Sky and Telescope.
People in the US have the May issue already in the mailbox.
Yes, mine came 2 weeks ago, although I get it electronically, so it didn't actually show up in my mailbox, but it showed, well, my electronic mailbox.
Cosmic Pow.
Yeah, Cosmic Pow. It's a really lovely shower there. So Cosmic Power Rangers.
Yeah, this is just the left part of the opening spread, right?
Yes.
I was very happy with this design. It's a beautiful opening of the story.
Yeah. Yeah.
Can you switch back to the first page?
Yeah, sure.
Because what I like about this illustration, it's obviously not a photograph, although the background is a photograph of the night sky, but the tiny white lines that you see is a graphic representation of what physicists call an air shower. So that's when a high velocity, high energy particle from outer space smashes into the Earth's atmosphere, and it strikes on the nucleus of an oxygen or a nitrogen atom. And then from the energy of the collision, this whole avalanche of secondary particles is produced, and that's what's being measured on the ground. So that's the topic of this story: cosmic rays, and then not just the normal kind, but the high energy ones.
Yeah.
And it is always funny to realize that cosmic rays is actually a misnomer, because it sounds like gamma rays or ultraviolet rays, which is electromagnetic radiation. But cosmic rays is not a wave-like radiation like the radio waves and the optical light that we know. It's just particles. It's high velocity, high energy particles.
Okay.
So cosmic rays is not a very good name, but well, it's stuck.
Well, Power Rangers is a pretty good name. I like that one. Very good. Did you come up with that title? Is that your title?
Actually, this was my suggestion, which is not normal. As an author, usually I leave the title blank because always editors will insert their own ideas. But
Right.
In this case, apparently the Sky and Telescope editor liked it.
That's a great name, Power Rangers, for this. All right. So, Albert, go ahead and take us away through the article.
Yeah, the thing is that cosmic rays is a very difficult. It's sometimes hard to understand, hard to grasp, but it's also a very exciting topic. And the reason why it's so hard is that you don't see them. This is you can imagine a particle like a proton, the nucleus of a hydrogen atom, zapping through the universe. That's easy, but usually here on the ground we don't measure these protons because they don't reach the surface of the Earth. They smash into, as I said, they smash into an atmospheric atom, and then we get all these secondary particles, which are not regular normal day particles, but these are short-lived elementary particles that may live for only a minute fraction of a second. They reach the Earth as a big shower, an air shower we call it, and then physicists use all kinds of equipment to detect this secondary shower. And that's one way to discover cosmic rays. Another way is that cosmic rays can produce gamma rays by smashing into an atom in the atmosphere. So then the energy of the cosmic ray particle is converted partly into electromagnetic radiation. And then you need other kinds of equipment to measure it. And what has always interested me is that this is an example where scientists use every possible means to get every minute amount of information out of what nature is providing us with. So it's really exciting in terms of observing technologies. But there's a big riddle because no one knows where the highest energy cosmic rays come from.
Right.
We know the lower energy ones, so that's the particles with less energy, slightly lower velocity, although they're all relativistic, meaning very close to the speed of light. But if they have low energy, they can come from supernova explosions. They can come from pulsars, these rapidly rotating neutron stars. They come from the sun. So we know more or less where the normal cosmic rays come from. But then there are these extremely high energy ones. We have measured cosmic ray particles. Imagine just one nucleus of a hydrogen atom with as much energy as a baseball during a match. A fast-pitched baseball, but that's a massive ball, obviously.
Yeah.
This same amount of kinetic energy, the same amount of energy, all get together into one tiny particle. That's really like a miniature bullet. And these cosmic rays are raining down on the Earth, and we don't know where they come from. They're not very frequent. The really high energy ones are rare, obviously, because they're the exception to the rule. And using the technology on the ground, we know that the highest energy ones have a frequency of about 1 per square kilometer per year. So if you have a detector of 1 square kilometer and you leave it working for a year, you have the possibility of detecting just one of these cosmic rays. So the story actually began just over a century ago, when people didn't know at all what cosmic rays were, and using a balloon, there was an Austrian physicist who discovered that the amount of cosmic ray particles became higher as he got higher into the atmosphere. So that's where the name cosmic rays come from. They realized they were from outer space. But these high energy ones, they were only discovered a couple of decades ago for the first time. And as my story tells, we still don't know where they come from. And the reason for that is that you cannot tell the origin from their direction. Normally, when you see light coming from the universe, like a flash of light, you know, oh, it's coming from that particular part in the sky. You can aim your telescope there and see what is beaming something towards you in that particular spot in the sky. But here it doesn't work, because the cosmic ray particles have an electrical charge. Protons are positively charged.
Okay.
Sometimes they're electrons, negatively charged, but most of the cosmic rays are protons or heavier nuclei. They have all a positive charge. And when they fly through the Milky Way, they are influenced by the magnetic fields in interstellar space. And there's not a very strong field, but there's a very pervasive field in the Milky Way, the structure of which we don't know exactly, but the magnetic field bends the paths of these particles. So when the particle arrives from the direction of one particular star, it doesn't mean it originated at that star. It kind of originated at the other side of the sky, and it made this tortuous random walk through the Milky Way before reaching us. So we cannot know where they come from. And that means that astronomers come up with all kinds of things to try to find this origin anyway. Now, here's the nice thing.
Sure.
The more energetic the particle is, the less it's being bent by these magnetic fields. It sounds more or less natural. If you're, it's like flying in the wind. The wind puts you every way, but if you're flying very fast, a breeze, a slight breeze doesn't push you away that very far. So for these highest energy cosmic rays, they're called ultra high energy cosmic rays. There, the bending by the magnetic field is not that particularly strong, and you can use the origin, the direction from where they are coming, and you know the real direction is maybe just 10 degrees, maybe 20 degrees in that region. There's some bending, not enough to find a particular source, of course, but you know what part of the sky they come from.
Okay.
And here's the interesting thing that started this whole study. People didn't know exactly whether the ultra high energy cosmic rays were from sources inside our Milky Way or from sources in other galaxies much farther away. Both could be possible. Now, if they are from our own Milky Way, you would expect that the ultra high energy cosmic rays would basically come from the region where we see our Milky Way band or our Milky Way nucleus, because their bending is not that strong. Okay. So it's like looking at the Milky Way with very unfocused eyes, make everything hazy to a degree of 20 degrees, and then you should see that pattern. And that was not what was being observed. People realized I think there's a graph maybe on the next page, a diagram, a map more or less, and no, one page further on.
Okay.
I believe, and yeah, there. One page.
There we go. This one.
And the top panel in this diagram is a map of the sky, like most readers of Sky Telescope will recognize. This is the whole sky rolled out into this ellipse. The gray part in the lower half of this upper diagram is the region that cannot be observed from the northern hemisphere. And here you see the arrival directions of dozens of ultra high energy cosmic rays. And you see they have a preference in a particular region.
Yes.
And that region happens to be in the constellation Ursa Major, the Great Bear. where there are a couple of active galaxies. And then the lower part in this diagram is from an observatory on the southern hemisphere. So we see the direction of origin for particles that were observed on the southern hemisphere of the Earth. Now the top part cannot be seen. And here you see that there's a preference for one part of the sky, which is not coincident with the galactic center. And this also means that it sounds logical that these ultra-high energy cosmic rays arrive at Earth from outside the Milky Way.
Okay.
You start to realize, where could they possibly come from? Is it from the environments of black holes in other galaxies? Well, maybe not, because almost every galaxy has a black hole, and then you wouldn't see this particular region highlighted. Or is it from starburst galaxies, where there's a huge amount of new formation of new stars with shock fronts and shock waves in interstellar outflows, and this can also accelerate these particles? Or is it from something else altogether? Or is it from a combination of sources? We just don't know. Cool. And that's the situation of the whole field. So the problem is, how can you find out? And one thing is, find more of these ultra-high energy cosmic rays. So make your observatories more sensitive. But here's the problem. If they're so infrequent and only 1 per square kilometer per year, you have to have a lot of patience, and you have to have a very big array of detectors to detect these secondary particles that we can observe. One of the biggest, actually the biggest cosmic ray observatory at present is in Argentina, southern hemisphere. It's called the Pierre Auger Observatory. It's named after a French particle physicist who did a lot of pioneering work in this field. And it consists of no less than 1,600 detectors. And I think there's a photo of one of them in the article. And these detectors are huge containers of highly purified water. This is actually not a detector in Utah.
One? There we go. Here's Pierre Auger.
Okay, here you go. Here's one of these big detectors on a truck, ready to be installed in the Argentina Pampa. And they have 1,600 of them spread out over an area as large as the state of Rhode Island or something like that.
Wow.
I'm not exactly sure about that, but it's very large. And these cosmic ray showers, these air showers, they rain down on a lot of these particle detectors because they move into the purified water. It's completely dark inside. And there, the secondary particle smashes again into an atom of the water, produces a small amount of light, and photodetectors on the inside of these containers, they detect these small flashes. And then we can find the direction of origin of the primary cosmic ray. We can say something about the energy, the total energy. We can even, if we combine this with some other kind of technology, we can even say something about the type of primary cosmic ray particle. And this array is being upgraded with additional detectors, with additional particle scintillators, with radio antennas to see the radio waves that are being produced during an air shower. And as I said, every possible way of getting this information out of the event is being used. So the hope is that this upgraded Pierre Auger Observatory will find an answer to the riddle.
What is the upgrade? Here in the article, it says 1,600 originally deployed. Are they planning an upgrade or?
Not in the number of containers. The upgrade is basically the addition of particle scintillators, which is another way of detecting particles. It's some sort of crystal material that produces tiny electric charges when it's being struck by an energetic particle. So the scintillators will be deployed, and then there will be these radio antennas, because when the secondary particles rain down on the Earth, they can also produce pairs of electrons and positrons. Positrons are the antimatter partners of electrons. And these electrons move in the magnetic field of the Earth, and they produce radio waves. because of their interaction with the. So it's a very complicated way that's being used.
Cool.
Now this is one hope.
Cool.
There's a second way of trying to study these cosmic rays when they interact with our atmosphere, and that's not from the ground but from space. And the funny thing is, from the ground you can only see part of the atmosphere. Obviously, you have these detectors on the ground, like in Argentina. You can study the air above you, maybe a couple of 100 square kilometers of air or something like that, but it's just a tiny part of the whole atmosphere, obviously. But when you're in space, you can study a much larger area of terrestrial atmosphere from outside.
Okay.
And you can detect the particles, because the particles rain down on the ground, these secondary particles, but you can detect the ultraviolet fluorescence that is being produced in the atmosphere.
Cool.
That's something that's also being studied from the Perroget Observatory, but only in this small part of atmosphere. But with a big satellite, you can see the whole night side of the Earth, and you know exactly at what wavelength this UV fluorescence will occur. You use a special filter, and you see if you see these tiny flashes produced by the cosmic ray particles. And it's one of the three things that's being described in my story. It's a future, hopefully future NASA satellite called POEMA. Big, expensive project, and later this year or maybe next year, NASA will decide whether or not to go ahead with it. And if possible, this satellite will study the cosmic ray events from outside the atmosphere. And then there's this trick that they're going to use. Very interesting. They use actually two satellites with big mirrors. So they move in tandem around the Earth, a certain distance from each other. And when something happens in the atmosphere, you have this parallax effect, and you can study it in 3 dimensions. So you can do the 3-dimensional reconstruction, and you also can try to find out where the original cosmic ray would come from.
Right.
And then the third way, and that's for the future, because only a prototype has been installed so far, and it was the reason for me to start writing this story, is a new development that's being tested now in China at a very high altitude. And I think at the last pages of the story, there are a couple of photographs showing, here you see the environment. It's just desert. It's high in on the edge of the Mongolian Gobi Desert. You see these mountain ranges in the distance. It's part of Tibet. Very high mountains, up to over 5,000 meters altitude. Sorry, I can't do the conversion in feet, but it's very high.
Meters is good.
And actually, they use these mountains as a detector. And this sounds extremely weird, but it's again gives you the impression of the ingenuity of these scientists. Here's the story. I hope I can tell it straight. When a cosmic ray particle enters the atmosphere, no, I have to start a little way back. When something energetic happens in the universe that is producing these cosmic ray particles, you expect it to also produce high energy neutrinos. Neutrinos are these very tiny, hard to discover particles that are being produced by nuclear reactions in the sun, for instance. You probably have heard that every second billions of neutrinos are streaming through your body. Nobody cares about it because we don't feel it. They don't do any harm. But these are all low energy neutrinos. But if there's a big explosion, or as I said, the environment of a massive black hole, or whatever the high energy cosmic rays come from, you expect also to have a production of high energy neutrinos. And now the funny thing is, neutrinos do not have an electrical charge. So they are not being bent by interstellar magnetic fields. If you could detect a high energy neutrino, you know where it comes from. You see exactly the origin of the direction of origin. If you see this neutrino more or less correlated with a high energy cosmic ray source, something that might produce these kind of things, you may be at the almost at the trail of the origin of the ultra-high energy cosmic rays, not by studying the cosmic rays themselves, but by studying the neutrinos that are being produced at the same time.
Okay.
Now, how can you study neutrinos? Obviously, with neutrino detectors that we know are in Antarctica and on all kinds of other places. But here we use the astronomers use something else. These neutrinos, if they come from a high place in the sky, they zap through a little amount of atmosphere and then through the Earth, and they are usually not being stopped. But high energy neutrinos, this sounds counterintuitive, but high energy neutrinos have a bigger chance of interacting with other particles. Because of their high energy, they have a bigger sphere of influence, so to say. So the chance that they are interacting with normal matter is actually larger for the high energy neutrinos.
Cool.
They do not pass through all of the Earth. They maybe only pass through a few kilometers of rock or something like that.
Okay,
now suggest that there's a source of high energy neutrinos low on the horizon. Actually, beyond these mountain ranges that you see here in the distance. The high energy neutrinos come towards you from outer space. They are approaching your measuring equipment, but they first smash into this mountain range. They do not traverse the mountain range because they have this high energy. They interact with particles in the mountain, and from these interactions, they produce, again, secondary particles. And some of the secondary particles are able to get out of the mountain and then produce radio waves that can be measured by these antennas that people are setting up. So it's a very complicated way. What the Chinese experiment, it's called the GRAND experiment for giant radio antenna for neutrino detection. And the GRAND experiment is an array of pretty simple radio antennas. It's just comparable to the old dipole antenna on your roof. A little bit more complicated, obviously, but it's a big array. And they study the radio waves that are being produced by the secondary particles that are the result of the decay products of high energy neutrinos that are being catched by these mountains in the distance. And if this works, and if we catch these high energy neutrinos, then we know their arrival direction because they're not being bent by magnetic fields.
Right.
And if we see more of them, they may be able to point us back to the source of these extremely energetic events that are also the sources of the high energy cosmic rays. Now, I hope I haven't lost most of my listeners, or your listeners, as you say.
I'm good.
And I try to write it up in the story in a way that I hope not to lose most of my readers. But I have to say the GRAND experiment, as I said, is just in the prototype stage. And eventually they hope to have not just one area like here in China, but on multiple sites in the world. You need an area away from civilization because you have to get rid of all artificial radio waves. It has to be a radio quiet area. It has to be a desert-like area, preferably very dry atmosphere. You have to have mountain ranges in the because you need the mountains as a detector. But people are thinking about setting this up in actually also in Argentina, which is a good place, close to the Andes Mountains.
Right.
Or maybe in Canada, close to the Rocky Mountains.
Okay.
Or maybe in what was the other place they were thinking about? Australia could be a place, or maybe Antarctica, although it's pretty expensive to build something there. So that's the plan for the future. And as you see, there are numerous experiments that are trying to get the answer to this riddle of the high energy cosmic rays, which are really the most energetic particles that we know of. Even our biggest particle accelerators, like we have here in Europe at CERN, they can only produce so much energy, and these cosmic ray particles are hundreds or thousands of times more energetic than what we can create here on the Earth.
Right. Very cool. Very cool.
Yeah, what is so exciting to me is the weird places that all these experiments are going on. I was lucky enough to be present at the inauguration of the Pierre Auger Observatory in Argentina in 2008.
Okay.
And it's really in the middle of nowhere. It's in this Argentina Pampa, sparsely inhabited. You have to, there are almost no roads. You have to use pickup trucks, all-terrain vehicles to reach all these water detectors. And I would love to go to China and to be on this high plateau and to see these instruments there and to realize that scientists are using all their ingenuity and inventiveness to solve the riddles of the universe that we are still struck with, because this problem is 40 years old and we haven't been able to understand where these particles come from.
Very cool. Well, I hope you get an invite to go to China, or maybe Antarctica if that's where somebody ends up building one, or the Atacama Desert if that's where it goes. That would be very cool. Well, Hobart, I want to thank you, very much for sharing your article with us and talking us through it. Let me ask, what's next in your writing adventures? You don't have to spill your next project, although you could if you wanted, you could.
Well, I can spill it. I think my publisher won't mind. I filed a manuscript for a new book. Some of the Sky and Telescope readers may know that I wrote a book on gravitational waves a couple of years ago, with all the new developments and the first detection all described in it. The book is called Ripples in Space-Time, and it was published by Harvard University Press and been translated in quite a number of other languages, including Russian and Chinese, actually.
Ooh.
So I'm happy with that. And Harvard University Press was happy with it too, and they asked me for a suggestion for another topic, and I filed my manuscript of a new book on the mystery of dark matter. And that book is will be published. It's now being in the editorial stage, and we expect to have it published by the end of this year. And it's a terrific, interesting story because it's so broad. It is astrophysics, it's particle physics, it's a lot of history, obviously, it's mystery, it's competition, it's riddles and mysteries. And because in the case of the dark matter, there is not yet a solution to. We don't know what it is, but when you will read my book, it will be clear that that studying dark matter has taught and learned us so much more about the universe already, and we only can hope that the mystery will be solved soon.
It's got all the elements of a great story. Very cool. Very cool. Well, and I'm also sure that this probably will not be your last S&T article. So look forward to.
I hope not.
Do well, stay strong and prosper. All righty, everyone, that'll do it. Overt, I want to thank you so much again for sharing.
You're welcome.
Thank you, everyone. We'll see you on the next one.
Okay, bye-bye.